Good afternoon, everyone. My name is Waldemar Ishibashi. I'm originally from Poland. I graduated from Poland with a civil engineering degree. After that, I went to London, where I was a civil engineer working for London Underground. I was building the new metro project. I was always interested in IT. I was always connected to that. I was always trying to force it on my bosses to use the newest technology ever. And at the same time, I met my wife, who's Japanese, and after we got married, we decided to start our life in here with her family. The goals of my presentation. This is a really brief lecture about machine learning. It's sort of like an initial phase entrance. There is some information on the slide that's sort of advanced, and the reason for that is I assume some people will look at it again when they have tiny bit more knowledge, so they can go and research tiny bit more. And I also want to show the road I've taken to learn tiny bit more machine learning. What is machine learning? Well, it's a field of study that gives computers the ability to learn without being explicitly programmed. So the big difference is normally when we design software, we provide the rules and the data, and then our program has pretty much the only way to work, and then we get an answer. Well, with machine learning, we provide the answers and the data, sometimes only the data, and then through our machine learning, we get the results. There are three main ways we can categorize machine learning. So the first one is supervised, second one is unsupervised, and there is reinforced learning. The supervised is where we provide both the data and the answer for that data. So the model is constantly checking whether the calculation is right every time it calculates it. And then unsupervised, the answer is not like the reason we do unsupervised learning is to divide the data into certain features. So let's say we have our customers, we want to know which one bought something from us, which one didn't. It's not a scale, it's just whether it's a yes or no, whether it's a cat or a dog. It doesn't have to be two, it can be multiple different types of data. That if you feed enough data, the algorithm will learn which type it's looking at. And then reinforcement is actually quite advanced subject. It's a combination of unsupervised and supervised. Another type of division is regression, classification, and dimensionality reduction. Regression is where we feed the data and we get the results. So let's say a perfect example would be a stock market. We have all the data from the stock market and we want to predict the price. Let's say, what's the price in 5 minutes? So then we can do our real life trading. Or if we feed in of photos, we can ask the algorithm what's the age of the person with what prediction. Well, with classification, as I said, we just get what type of data we're looking at, whether our client is likely to buy from us or not. Or let's say whether for medical data, it's often when we check the blood and we know that the person has a cancer, from all other data we have about the patient, we can predict which type of cancer it is. This is where it's used for. And then dimensional reduction is the whole bunch of machine learning algorithms that help prepare the model for further machine learning. Like checking from photos. Like we say we have a bunch of photos mixed from the internet. We want to recognize the face to do further operations on those faces to check what type of face it is. So this is where the dimensional reduction functions comes in. Machine learning flow. But first, obviously, we need to train the data. So usually from the whole data we get, we take around 80 to 90% of data to our training. We train our model, and every now and again we validate our model to check which works. And it's all from a first bunch of samples. because with machine learning, different models work with different accuracy. So we need to validate that data while retraining the model. This is where engineers come over to fiddle that model, to check what is perfect. And then testing the model doesn't change the model anymore. It's literally the last stop before giving the model to the client for us to check whether we've done a good job or not with our model. Data effectiveness. Data is very crucial in machine learning because the model learns on our data. There's something called underfitting bias, which is a perfect example is the stock market. If we provide only a few models and we want to predict it for a week in advance, obviously not going to do a good job. And then overfitting happens when we provide too much data and the models start finding patterns that do not exist there. So then the results will be not realistic. So that would be an example of reality, which is just two groups of samples. The good model will obviously never be perfect as the reality, but our model will figure out the division somewhere here. And if we provide the data with too much bias or too much noise, the model may start struggling. Also, our model is not a perfect example. It doesn't have to be perfect example of reality. For example, for Gmail and spam, for the model, they don't have a real life balance between spam and real mail, because then the model will struggle to learn. So they overfeed the spam, let's say 20 times. So the model learns exactly what spam is, how important spam is, and then if every now and again the model will think, oh, this is spam, but it's not a big problem. Bigger problem is if it's not spam, but it is spam. Also, a more risky scenario is recognizing cancer. We giving the model a real life scenario where we want to predict the cancer. We need to really think about what the goal of our model is. With cancer, if we get too many false positive, it's not a big problem because we can do further tests and we can say, okay, our model didn't predict it appropriately, but we know our customer, our patient doesn't have a cancer. The bigger problem is if our model will be very sure that that person from that data doesn't have a cancer, but in reality it has a cancer. So the model and the preparation of the model and the understanding of the model is really important to create a good model that works in real life. That's, I think everyone possibly knows that picture. That's a simplest neural network with just 3 inputs, one hidden layer and one output. We call these neurons, and they're not exactly human neurons. These are the ones that calculate the little functions, and the input is types of different functions. Deep learning is something that comes up in pretty much every article. The only difference between neural network and what people call deep learning is the addition of a hidden layer that adds complexity to the model. So with the same functions that we're feeding, we can get a completely different way of thinking of the model. As the website I wanted to show, this is made by Google. That's the address of the website and the information will be provided further on. I've spent, I think, 4 hours on that website to understand what a neural network is. The reason for that is because it's visual. And I want to also explain how a neural network works tiny bit on it. So this is a play button. Obviously, the epoch is the amount of rounds that the neural network does explanation. For a model, we can add a learning rate. The faster the model learns, usually the worse the result is. The slower it is, it can overfit, so it can find things that don't exist in our model. So there is a balance between all of that. And on a beautiful website, we feed our data, which in that case is in there. So our data is just recognizing which dots are where. So our orange dots are outside, our blue dots are inside. We can fit features, which is what functions our model fits, how many hidden layers we have, and how many neurons we have. If someone wants to really visualize how neural networks and machine learning works, this is the first website I would suggest to play around with. And it's good to learn also how a model learns when we add certain stuff, because I used to think when I start, the more complicated, the bigger the model, the cooler it is, obviously, and also the better it works, which is not exactly how it works. Sometimes with only one model, we get really good results. So if you see in here, it's 6 epochs, which is 600 times the function has to go through. With just one added, one neuron added, it's 200. And the results are really good. And this is an example where if you think if you make your model too complicated, the answers may not come up, because the model will try to find something that doesn't work, doesn't even exist in reality. So really strong advice to play around with the website. And then for that model, this is a perfect spot. It learns really quickly and efficiently. And if we make it too simple, it doesn't learn. And also, what I was thinking before when I was learning, so I was thinking, how is that the model knows what's a good answer? So the good answer is in weights. If the function creates an appropriate answer, these weights will go heavier, which is they go bigger, which is the way machine learning works. It tells the model what you're doing is right, so what this one is doing is right, what this one is doing is wrong, do more of what's right. And that will be an example of machine learning hello world. And the point of that is to figure out the function, what y we need to get appropriate, to figure out the function. I will explain it later on. So when we feed x -1, we want to get -3. So how do we do that? How do we do it without having the function itself? Well, originally, normally what people would do is take -1, and okay, we need to get -3. So what's the y? So the y in that example would be possibly 1.3, because it fits the model. And then we go, okay, it's -3, we go to our next example. If we fit -3, it doesn't really work for this one. So this is where our weight comes in. We go back and say, okay, this is not exactly how it is. Let's continue further on learning. If we fit 0, we're getting -1. So what does it mean? Well, it means the -1 is possibly 0 plus something. So that plus something will be, in this case, -1. So now we know to get a y, we need to do something with an x and then take -1 of it, and we're going to get our answer with reasonably good prediction. So if we go further, we get 1 and 1. So how do we do? Well, we have more data because we already did some calculations. So if we take our y, which is 1, and then we have an x, and we're getting -1, which eventually results in our x equals 2. So eventually we can figure out that y is 2x -1. And the crucial lesson from that is, for me to figure that out, I need to take my first example, -1 and -3, do some calculations, check how it works, and then go back. And then further continue doing my process. And I'm literally learning, and this is where machine learning comes in. The machine learning does one prediction and then goes back, takes further data, and then do another prediction. And then as they go along, if the model is done correctly, we get a model that can predict within reasonable accuracy how good our model is. And that's how it looks like in Python. We import TensorFlow to Python, and we import NumPy, which does operations. And then we create a model, which is one neural network, one layer with one neural network. We feed our data, and I have additional data to make it way quicker. And the magic happens here, and we're literally fitting our data to our answers. We're squishing them back together, and then our model trains itself pretty much, and we're just giving the answers. And that's the links I want you to have. That helped me a lot. There's a lot of information on the internet that's very vague. So this is sort of, if someone does those steps, they can have a nice roadmap of how to learn. And I want you to have also some shortcut to do this Python exercise, because actually, if someone never did Python, that takes quite a long time to set everything up. So that's just for you for the future. And this should be my last. And that's the end of my presentation. I'm not sure why it doesn't load right now. Thank you very much.